Hi, Chris Good here, and we're going to do a quick video on how to solve our sample analysis of variance that we did in class in February. So here are the made-up Mozart effect data that we were talking about in class, and these are the scores from the Mozart group, the relaxation group, and the silence group. So the first thing we're going to do is get means for each one of them by taking the average in each group. And we can just select those data, right, and then copy and paste those cells to get means for all three of our groups. So the trick with ANOVA is to find out if there's a significant difference somewhere among these means. And we need to compute three things. We need to compute the sum of squares within treatments and the sum of squares between treatments, and these are just two parts of the total variability in the entire group. We're going to compute all three of these, even though you really only need to do two of them, and you can get the third one by subtraction or addition. In order to compute these, we're going to need to know the grand total of all of the scores. That's what G is. So you can sum all of the scores to get G. We need totals for each group. That's what T is. So T is just the sum of the Mozart scores. Don't include that mean in the sum. That's not a score. And we'll just copy and paste that. We also need to get the number in each one of these things, right? So that's just a count of the scores here. I know that there's only 5, but if you use count, it's going to be a lot easier, I think, in the long run. So we can do that. In order to compute F, we're also going to need degrees of freedom total. Well, we don't use total, but we need degrees of freedom within treatments. You know what? I'm going to switch these just for now between treatments and sum of squares within treatments. It just makes it easier because they are the numerator, the variance between treatments is the numerator, variance within treatments is the denominator. So let's just be consistent with that. Okay. Let's move these over a little bit and format not sum. Okay. Total sums of squares we're going to get by calculating the grand mean. So I'm going to do that here in the corner. Don't get G confused with grand mean. This is just the average of all the scores. Average of all of the scores. Okay. We can compute deviations, right, for the entire thing. I'm going to do them over here just so we can compute sum of squares total. I need a little bit of room because I want to, there we go. Okay, so these are deviations from the grand mean. Alright, so I'm going to do this for, it's going to be for Mozart, relaxation, and silence. Deviations from the grand mean aren't going to really reference what group people were in, right? It's just their score minus the grand mean, and we want to make sure that we're going to do that as a static reference by putting the $sign on the correct side of both the column and the row designation. Okay, if you do that, you can copy and paste for all 5 scores and all 3 columns. Let's do it this way. Alright, that gives you deviations, and these are deviations squared from the grand mean. You just square these. Okay? Again, copy and paste is your friend. Let's remember where these guys came from, okay? Okay, so the total sum of squares is just the sum of all of the squared deviations of all of the scores from the mean of all of the scores. And that's sum of squares total. Okay, but we also want to get sum of squares for each individual group, which means we're going to need to compute deviations for each group. Now, keep in mind how this is going to be different here. Okay, so for the Mozart group, it's the deviation of the Mozart scores from the Mozart mean. Oops, from the Mozart mean, and we want to put that $sign there to reference that statically. So those are deviations from the Mozart mean. We're going to compute deviations of relaxation from the relaxation mean, right? And we want to make sure that we reference that static mean. And deviations of the silence mean, or the silence scores from the silence mean. So put that $sign there, $. We can copy and paste these all the way down now, and they will do relative referencing all up the column. And we can sum these, so we need to square them first. And these are going to be deviations squared for each group. It's the deviation of these scores from the means within those groups. So this is the Mozart score raised to the second power. And when you copy this, you can just paste this and it'll square everything referentially just fine. Sums of squares then is equal to the sum of the square deviations for the Mozart, and then when you copy and paste this, it's going to sum those square deviations there. Let's just check and make sure that's true. So we sum the square deviations for the relaxation group. There we go, 6.8, 11.2, and 9.2. Those are sums of squares for each group, and if you add them all up, you'll get the sum of squares within treatments. So we'll add up all the sums of squares within treatments, right? So that's our sum of squares within treatments. We can actually get between treatments sum of squares by subtraction. It's just the total sums of squares minus the within treatment sums of squares. But I'm going to compute it another way. Let's just remember though that it's 12.4, okay? 12.4 on sum of squares between treatments. If you ever get stuck, you can just go to the ANOVA formula sheet and remember that sum of squares within treatments is the sum of all the sum of squares for each treatment, and you know how to do sum of squares within each treatment. This is the new formula. This is what might give people trouble, but I am totally going to ask you this in later assessments, so please remember how to do this. It's the sum of t squared over n minus g, and then you square that, divided by big N. Sum of t squared over n. What is t? Well, t is just the total within each group. Remember, that's the sum for that group. So what I want to do is get a t squared, and that's going to be this t here, and we're going to square that. Square the other t's, and then we can do t squared over n. Right, that's just t squared divided by n. And if we sum all of those, that's the first part. That's this part right here of sum of squares between treatments. But then we need to subtract g squared over big N. Let's remember that big N equals 15 in this case. Let's put this in the right place, shall we? Okay, and g squared over n is equal to, I'm going to put this in parentheses, g squared over n, 194.4. So now we can get sum of squares between treatments. I'm going to compute it right next to the one we got by subtraction. So this is going to be the sum, I'm going to put these in parentheses, right? The sum of our t squares over n minus our g squared over big N. Look at that. It's also 12.4. So you should be able to get sum of squares between treatments two ways. One, using this formula that I just showed you, sum of t squared over n, this is t squared for each group divided by n for each group, and then you subtract the grand total, that's the sum of all the scores, and you square that divided by n, subtract this entire quantity. And you can also get it by, if you're given total sum of squares and within treatment sum of squares, you can get it by subtraction, because total is always going to equal between plus within. But we're trying to get to f. We're trying to see what f is. And f is going to be the mean squared between treatments divided by the mean squared within treatments. We haven't computed these yet, but mean squared is the same thing as variance, and variance is sum of squares divided by degrees of freedom. We know that between treatments degrees of freedom is k minus 1, and our k here is 3 because we have 3 groups, right? And we know that from our formula sheet. K minus 1 is between treatments degrees of freedom. So between treatments degrees of freedom is k minus 1. Within treatments degrees of freedom is big N minus k. I'm just getting that right from the formula sheet. Big N minus k within treatments degrees of freedom. Okay. Mean squared is variance, and variance is sum of squares divided by degrees of freedom. Make sure between divided by between. And here, once again, mean square is sum of squares divided by degrees of freedom. And we have our mean squares there. F is just the ratio of mean squared between 2, mean squared within, and there's our F value. Now, what we didn't do in this case is look up our critical values. In order to do that, you need both of these degrees of freedom, right? So our critical values at 2, if F crit at 2 and 12 degrees of freedom, for guess what, an alpha of 0.05, and it's two-tailed. Actually, there's only one tail in F, so you can't do two-tailed. Let's go look up that critical value. So where are we? Here's the F distribution. Here's degrees of freedom in the numerator, and we had 2 degrees of freedom in the numerator. Here's degrees of freedom in the denominator. Here's denominator, and you'll notice, which one do we use? There's 2 numbers here, 3.88 or 6.93. Entries in light phase type are critical values for 0.05. So we'll use the entry in light phase type for 2 and 12 degrees of freedom. F crit is 3.88. 3.88. Well, observed is 2.735. F crit is 3.88. So if this here is 3.88, 2.75 is here. It's not in the critical region. So our decision here is to fail to reject. We did not detect a significant difference among these 3 means, F2 and 12 degrees of freedom equals 3.88, and P in this case is greater than our alpha, 0.05. That's it.